In a previous presentation, we gave an overview of a technique that employs lasers and optoelectronics to induce a net force on a given target. In this presentation, we'll discuss a couple of key applications of the technique and suggest how it may be enabling for the aerospace industry. It costs thousands of dollars per pound to deliver a payload into low Earth orbit. That often sums to tens or hundreds of millions of dollars for a given satellite. And once in orbit, its days are numbered. Even several hundred miles above the Earth, atmospheric drag will slowly degrade the orbit of any satellite. Many satellites carry propellant to provide the occasional boost against atmospheric drag, but few are commonly refueled. And once the exhaustible onboard fuel is spent, the satellite will inevitably fall and burn up on re-entry. But if a satellite is equipped with a set of solar arrays that drive an electro-optic system to provide a renewable motive force, that motive force can continually compensate for the force of atmospheric drag. With this approach, a device requiring just tens of watts of electrical power could significantly prolong the operational life of satellites in low Earth orbit. Let's consider a specific example. The International Space Station weighs about 400,000 kilograms and orbits about 400 kilometers above Earth's surface. It has an orbital decay rate of about 2 kilometers per month and requires 7.5 tons of chemical fuel annually to offset that decay rate. That constitutes a continuous energy loss of about 3 kilowatts and implies $200 million per year in refueling costs to maintain orbit. The solar arrays on the International Space Station produce a total of about 100 kilowatts of electrical power, meaning that a system that could convert 3% of that energy to motive force could save $200 million per year in refueling costs. Let's consider another possibility. The cost of achieving a low Earth orbit may be thousands of dollars per pound, but the cost of reaching geosynchronous orbit can be 6 to 8 times that. If an electro-optic system can provide sufficient motive force to compensate for atmospheric drag, then any force in excess of that can be channeled to lift. Over the course of weeks or months, that relatively small but renewable and sustainable source of lift can drive a satellite from low Earth orbit to geosynchronous orbit for only nominally increased cost. Still, we can do better. We can imagine a separate craft with significant excess lift capacity, dedicated to ferrying satellites in low Earth orbit up to geosynchronous orbit. This may occur over the course of months or even years, depending on the payload. But ideally, a separate craft could serve the role of an orbital tug. Once the payload is delivered, the tug could return to low Earth orbit, pick up another orbiting payload, and repeat the process sequentially. Again, this could dramatically reduce the cost of achieving geosynchronous orbit. When we can significantly reduce the cost of climbing to the edge of Earth's gravity well, the next step is that much closer.